Welcome to The Explainer. Today we are looking at a literally historic shift in how we actually learn about the universe. For generations, physics had this reputation, right? It was kind of rigid, super intimidating, and honestly, pretty inaccessible. But right now, we are smack in the middle of this incredible transformation. We're moving totally away from those isolated traditional classrooms and stepping into a wildly dynamic, fully connected educational ecosystem. Let's dive into these sources and see physics in a completely new light. Okay, let's dive into this. Historically, learning physics was, well, it was a math-heavy gauntlet. You're talking passive reading, ridiculously expensive textbooks, and rote memorization of formulas that just felt completely detached from physical reality. But contrast that with the modern ecosystem we have today. It's vibrant, it's open access, and it's totally driven by active inquiry and experiential prototyping. It isn't just about memorizing equations anymore, it's about actually touching, seeing, and experimenting with the literal forces that govern our world. To really grasp this, we're going to explore 4 distinct biomes making up this new modern physics ecosystem. First, foundational texts. Second, digital sandboxes. Third, media and storytelling. And finally, tactile prototyping. Starting us off with biome number 1, open access foundational texts, democratizing the curriculum. Now, what's really interesting about this slide is how that massive financial barrier of traditional textbooks has just been completely dismantled. Look at the sheer accessibility of world-class knowledge here. You've got platforms like OpenStax giving out rigorous, peer-reviewed AP and college-level textbooks for free. Then there's the physics classroom with active, self-paced tutorials for high schoolers. We've got hyperphysics for undergrads, and even the legendary Feynman lectures for the advanced folks. The core curriculum is no longer locked behind a $200 paywall, guys. It's modular, global, and completely free. Let's zoom in on one of those for a second. Hyperphysics, built by Georgia State University. The brilliant thing here is that it lets you completely ditch linear reading. You don't have to read chapter 1 to get to chapter 2. Instead, it uses this interconnected neural network of concept map cards. It lets you organically trace the physical and mathematical links between broad concepts, like classical mechanics, right down to highly specific modern subfields. It completely rewires how you map out your understanding of the universe. And hey, for those of you pushing into really advanced territory, we have the absolute peak pedagogical standard, the Feynman Lectures on Physics. This is Richard Feynman's 1960s masterclass at Caltech, and the whole 3-volume set is now just sitting online for free in high-res HTML5. What makes his legacy so incredible is his methodology. He prioritized building a deep physical intuition and using brilliant everyday analogies over just mindless number crunching. He constantly challenged his students to critically question those underlying theoretical assumptions. It's just a phenomenal resource for advanced self-directed learning. Moving right along to number 2, interactive digital sandboxes, making the invisible visible. This brings us to the PhET Interactive Simulations Project. Founded back in 2002 by Nobel laureate Carl Wieman, the core design principle here is something called implicit scaffolding, and it's brilliant. Rather than explicitly telling students exactly what to do, the simulations provide this dynamic guidance that naturally encourages open-ended experimentation. By manipulating virtual voltmeters, stopwatches, or sliders, you get immediate visual feedback. You are literally making invisible forces visible. It's an amazing way to build incredibly solid conceptual models right in your own mind. Let me actually guide you through a fantastic example of this interactive loop using an O-physics simulation of sound wave interference. So step 1, you adjust the frequencies for your left and right ears so they're just slightly different. Step 2, you run the simulation. Step 3, you immediately visually observe the oscillating amplitude while simultaneously hearing the volume swell and fade over time. It creates this awesome auditory phenomenon called beats. This active manipulation completely transforms abstract wave math into a real sensory experience. And this brilliantly illustrates how gamification takes this interactive modeling even further. We're literally seeing commercially successful video games being used in formal classrooms. Take Kerbal Space Program, which is actually endorsed by NASA. Players run a space center and have to deal with real structural constraints and actively navigate Newtonian mechanics and calculate escape velocities just to build rockets. Or Universe Sandbox, where you model n-body gravity or alter Earth's axial tilt to watch climate feedback loops happen in real time. It just makes the massive astronomical scales of physics incredibly intuitive and completely hands-on. That brings us to our third biome, media and storytelling, humanizing the science. We have this incredibly diverse roster of digital storytellers out there doing amazing work.
You've got YouTube channels like Veritasium using real-world demonstrations to expose these deeply ingrained counterintuitive misconceptions, or Minute Physics using whiteboard animations to casually explain quantum mechanics in 5 minutes. In audio, there's Star Talk, blending astrophysics with pop culture, and podcasts like Daniel and Jorge Explain the Universe, where they tackle profound cosmological questions like dark matter and white holes, but without any of the intimidating jargon. They humanize the science. They make it accessible, relatable, and deeply entertaining.
46. That is the exact number of curriculum-aligned episodes in PBS Digital Studios Crash Course Physics, hosted by Dr. Shini Somara. This beautifully animated series covers the whole shebang, from basic straight line motion all the way out to astrophysics and cosmology. It's just a flawless example of how high-quality video media can give you a comprehensive, super engaging walkthrough of an entire high school-level physics curriculum. Finally, we arrive at number 4, hands-on tactile prototyping, anchoring theories in reality. Let's move to and see how this builds a crucial hands-on foundation with the Exploratorium Science Snacks. These are teacher-tested DIY projects made with cheap, everyday materials. For example, the bicycle wheel gyro lets you literally, physically feel the bizarre forces of angular momentum and precession. The eddy currents project, you drop a magnet down a copper pipe to demonstrate Lenz's law. They even have a setup where you build a working speaker out of a paper cup and some magnet wire. Despite all our digital advancements, letting students physically feel the forces of physics in their own hands is absolutely crucial.
And honestly, this tactile, experiential philosophy has deep, deep roots in historic physics pedagogy. Just look at the legendary MIT classroom lectures of Professor Walter Lewin. To prove that the period of a pendulum is independent of its mass, he notoriously swung across the lecture hall on a 5-meter cable. To demonstrate Newton's laws, he literally rode a tricycle propelled by a discharging carbon dioxide fire extinguisher. These highly visual, physically demanding classroom anecdotes really prove the enduring power of showing physics in the real world.
But hold on a second, because we have to introduce a vital moment of tension here. Educational researchers actively warn against a trap known as pseudo-teaching. This is a classroom environment where students feel like they're learning because the lecture is highly entertaining and visual, but their actual conceptual retention remains incredibly minimal. Think about it. Passive entertainment, no matter how engaging the explosion or the crazy pendulum swing is, does not automatically equal deep scientific literacy. So the crucial point is that we absolutely have to move from passive video watching to active learning. This entire amazing ecosystem we've been talking about, it only works if we pair those high-energy demonstrations with active methods. Things like interactive lecture demonstrations, or putting gap questions into videos that force a student to pause and answer before moving on, or using peer instruction. Students have to be challenged to predict, discuss, and physically test outcomes if they want to truly anchor that knowledge. So I want to leave you with a direct challenge today. Knowing the very real dangers of pseudo-teaching, and knowing that just passively watching a screen is not the same as actual learning, how will you actively test the physics of your world today? Seriously, don't just take my word for it. Step away from this explainer. Go find a pendulum, drop a magnet, or boot up a simulation. Get out there and actively experiment with the incredible forces that literally surround you.